right. Morning, everyone.
Good.
So we're going to pick up where we left off, and today we're going to get to actually talk about if and while, which are a little bit interesting because of course Jack has if statements and while loops, and the virtual machine does not. Right? All it has is goto. So after doing this, you're going to be very, very glad that high-level languages give you things like if and while. So let's see, where were we?
Expression.
Yeah, I think we'd started talking about expressions. So yeah, we were kind of in the middle of right. We were doing compiling a statement, and we said, okay, if it's a let statement, we can compile a let statement, and we figured out how that worked. But then we needed to compile the expression that is on the right side of the let. And obviously, compiling expressions is something we're going to be doing a bunch. I mean, like, if you have an if statement, what's that thing? That's an expression. If you call a function, what are the things that go here as the argument? Those are all expressions, right? So there's a whole bunch of places in the grammar where you can have expressions. And remember, the interesting thing about expressions, I'll repeat, I said this kind of right at the end of class last time, but I'll repeat it so then we can get into writing the code, is that expressions is the one place where, let's see, where is the, yeah, so this is all the grammar for expressions. And an expression has a bunch of terms separated by operators, right? And term could be any number of, all these things. And we specifically noticed that there's multiple places where you could have an identifier, like a variable name, but you have to then look at the one next token to figure out what you're doing, right? So you could have a variable name followed by some brackets. That's an array index. You could have a variable just by itself. You could have a variable which is a function call, or you could have a variable which is the name of an object or a class, which is followed by a dot and then a function call. So, last time we kind of started out just using the tokenizer the way that we had done it before, and then realized halfway through that it was going to be really annoying, and we kind of redid a little bit, or added some things to the tokenizer so that we can do this peek thing where we don't actually like get the next token. We just say, what is the next token? Leave it there, but I just want to know what it is. We're really gonna want that now, because if we have to look like an extra token ahead, it's gonna end up being super annoying, because if you see a variable and you're like, okay, the next thing is a variable, what's the next token after that? If it turns out to be like, maybe it turns out to be like a plus, right? And it's like, oh gosh, now that was going to be the next, op in this, but that was inside of a loop that was reading in terms and ops, and now I've read that token in, so now I've got to somehow like pass that back. When I return from this, I've got to tell it that I read its plus. So sorry, but here it is. That's going to be super annoying. So the ability to just peek at it and not mess up anything else that might want to read that is going to be really helpful. So. Let's we'll do this. So we can have that on the screen, and then we can. Okay, so to compile an expression, we're gonna compile a term. Right, because an expression definitely starts with a term. And then there might be an operator followed by another term, or maybe not. So we're going to just peek at the next thing. So, and we'll say like if t is an operator, then we're going to, I guess if it's a binary operator, well, I'll just say if it's an op. Then we're going to
we're going to actually read that. We'll actually read that token, it's the operator, and then compile a term, and then we need to do the operation on those two terms, right? So this would be, imagine if we had like 3 plus 5, we compile the 3, which is going to push 3 on the stack. We notice that we have an operator, so we'll compile the next term, pushes the 5 on the stack, and now we do the operation. It'll do that operation on the things in the stack, right? So I'll just say like, well, we could, probably what we want to do at this point is we just say, you know, emit, you know, opcode code. Like if we have some dictionary, opcode is a dictionary from ops to VM code. Because I think every operator is going to correspond to a single line of VM code. So, you know, if it's a plus, it's just add. And if it's a times, then it's like a call, you know, math.multiply to or something like that, right? And we kind of did this last week when we made our simple compiler for this kind of Lisp language. We did the same. We had a dictionary like that. I don't remember what we called it, but that's fine. All right. Any questions at this point? Just what we're doing, or okay.
What are we gonna do with the unary operations?
With the unary up, yeah, where do those show up? So they show up in a term, right? So basically, yeah. Let's write compile term next. When we do compile term, we want to, we can read a token and then see what it is. And if it's a unary op, then we do that case where we do that, right? And if it's an identifier, that's the special case where we have to read one more. We have to peek at the next token to see what we're actually doing, right? So this is compile term. I think we actually said we had like a function called next that gets the next token. So I don't think I'm not gonna write like all the cases because that'll leave something for you all to do. But I definitely want to talk about the case where we get an identifier, because that's this funny case where we have to look at one more token. So if t dot token type is identifier, or I'll just say if t is an identifier, then we can say, you know, t2 we would peak, and then we can say, you know, if and at this point, right, if t2 is, you know, what are the possibilities? It could be a bracket, right? Then we're going to compile array access, something like that. If t2 is a dot, we're going to compile, well, I guess I have to pass it t, right? Because if I'm compiling an array access, it's like, well, I need to know what that identifier was that was the name of the array. If it's a dot, that means I'm compiling a this is like a, I don't know what to call it. It's a subroutine call, but we have two different kinds of subroutine calls. I'll just say a dotted subroutine call.
elif, if it's a parentheses, we're going to compile a normal subroutine call. And then otherwise, right, in any other case, it means that, the next token is not actually part of this term. It's just like something in the next term. And what we actually have is just a bare variable name by itself. Like if we said x plus 5, we would see the x, and then we would peek at the next token, and it's a plus. So we're like, that's something else. We're going to leave that alone. We're just going to, so in any other case, we're basically going to say, we're going to emit a push, right? It's something like, because we just have a variable, so we just want to look up that variable in our symbol table, and we just want to push onto the stack from whatever, right? So we'll push, segment offset. I'll just say like look up segment and offset for variable. So let's look over here and we'll just think about what kind of VM code we would actually end up with. Okay, the dot 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 is, right, so these two lines together are the let statement. So we're first, the dot 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 is the expression. We're going to compile that expression, and then once we've compiled the expression, the pop local 0 is taking the value that ended up on the stack from that expression and putting it in the variable value. So in this case, we're going to end up with something like, first it's going to compile that call to keyboard.readchar, which is really just going to turn into something like call keyboard.readchar 0, something like this. Right. And then we're going to say push constant 77. That's how we'll compile the 77. And then, we didn't write those. That would be like, I guess I should have said like, there's a whole bunch of elif, whole bunch of cases for the other things that an expression token could be, right? It could be an integer constant, in which case we would say push constant, whatever. It could be a string constant, it could be keyword, right? We'd have to handle all those things. But, and then finally, we would do the subtraction, right, would come from, from here. We would see that operation, we would compile both terms, and then we would emit the code for subtraction, which is just going to be so. Okay, any questions about that? Okay, I don't think we need to talk about expressions anymore. I will leave you the joy of filling in all the details of getting expressions to work. But of course, you don't have to do it all at once. So just do a little bit to get each test to work, and then do a little bit more. So not too bad. So what I really, okay, and then the do output.print line, I guess we haven't, I don't think we literally wrote pseudocode over here to handle do, but it's pretty simple, right? It's just like, because if you have a do, where is that? Oh, do statement. I don't think I actually wrote down the syntax for a do statement, but I think it just has to have a function call. I don't think you can have anything other than that. Yeah. Do, it just has the key, the token do followed by a subroutine call. And you also need to compile subroutine calls for expressions, so that's just going to turn into, call output dot easy peasy. Compiling subroutine calls gets more interesting when you have,
You know, in the cases where you have like,
basically when you're calling methods. So if you're calling, if you have like an object and you're calling a method on the object, so you have like, you know, circle dot whatever or something. That's a little more interesting, and we're going to talk about that next week when we talk about classes and object stuff. But for this kind of simple case where you just have, I think right now this is the only kind of case you have to handle where you just have the name of a class dot some function that class defines, and then all you have to do is just say call that thing. All right, let's talk about the if. So how is this going to work? And maybe, I mean, there's a couple ways we could do this. Maybe, yeah, let's do this.
let's think first about what kind of VM code that we want to generate for this. And then we can think about writing some pseudocode that would do that. But, right, the point, of course, is that, you know,
VM code doesn't have ifs, so, well, it does have, it has an if goto, right? That's like the only thing we can do. So what do you think? What would be like the first VM code that we would have to generate for this if?
The expression.
yeah, so the first thing we'd have to do is compile that expression so that it evaluates the test to see if it's true or false.
Okay, so this would be, so here's the if test. So it would be something like, you know, it would say, first we're going to push the value of, well, the value of value. We would push the variable value onto the stack, which is say push local 0. Then we would push constant 0, and then we would say LT. Okay, so we now have on the stack,
you know, whether value is less than 0 or not. What should we do next?
I guess if go to.
so we do it like an if goto. So where do we want to go to if
It's true.
or what do we want to do if it's true?
True.
Stuff inside the main if bracket.
Yeah, so if it's true, we obviously want to do, it's not on the screen anymore.
But yeah, you all know how ifs work. If it's true, we want to do, you know, this thing, do output.print it true.
But if I say if goto, so if goto is gonna, you know, I can give it a label, and it can jump there if this is true. And if it's false, it's not gonna jump, it's just gonna continue. Okay? So if we do it this way, this is gonna be awkward, because it means that the code for the true, for the then part of the if, is gonna have to be somewhere else. And the code for the else part is gonna have to be right after the if goto, in the opposite order of how they are in the if. That's gonna be awkward because it's, generally speaking, as we're parsing through the Jack code, we're kind of generating VM code as we go. And if we did that, we couldn't do that anymore. We'd have to like save up some VM code and then like emit it later once we got there. So you could make that work, but let's do something else. So any ideas, how could I make it so that I actually have the code for this part come first, and then the code for this part come after that?
Not.
Cookie?
Change the less than
Mm-hmm.
to like not less than. I don't remember how you do
Yeah,
that.
yeah.
But like make it so that
Like invert the...
it's only false when it's less than. So you just keep going.
Right. So you want to like invert the test basically, so that we'll actually end up jumping when the test was false instead of when it was true. Does anyone remember how would I do that? How would I make the opposite of that test?
Not.
Oh, yeah, so, okay. I can just put, right.
So you might say, oh, greater than or equal to. Well, the VM doesn't support greater than or equal to, only less than or greater than. But we can say not. And not, right, not is the VM operation that just says take whatever's on the top of the stack, invert it, and put it back. Right, so we're doing this so the then branch, then code can come first. So if we want to jump to the else part, if the test was false. Okay, and I need to say, you know, if go to, and then I need some label, right? So, you know, and I can make up whatever I want, honestly. The only thing, of course, that I have to be careful about is, you know, I might have lots of if statements in a .jack file, and I need to make sure that all of their labels don't conflict. And we've done this before, right? So you can do this same kind of thing where like you keep like a global counter, and every time you have to generate one of these labels, you increment the counter and like stick that number on end or something. So maybe we'll call it like, you know, if else, you know, 1, something like that. So somewhere down here, I'm going to have label if else 1. Okay. Okay. Now what? I guess I still.
I guess now do call.
What was that?
I guess now do call.
Yes, and now we do. Let's see here. There we go. Now we can see both at the same time. So this is the Jack code. Yeah, so the code for, you know, whatever code is for all the statements inside this part are going to go right here. So in this case, we're just going to say call output.print. Oh, no. First, of course, when I compile this, I'm first going to compile this argument, right? I compile each argument, and then I call the function. So we're just going to say like, how do I compile true? 1? I don't think it's 1. Yeah.
-1?
Yeah, it's actually, the VM represents true as -1. So I think we should be able to say, actually when you say push constant, I don't know if you can put a negative there. Can you?
Push 0, push 1 sub.
Yeah, you could do that, or you could push 1 and do neg, right? I'm actually, okay. I kind of,
I think you can't put -1 into the A register.
you can't put it in the A register, what do you mean? I mean, you can definitely have negative numbers. It's just the question is, can we use negative numbers in the syntax of the VM? Push pop commands, push segment index. Index is a non-negative integer, yeah. Okay, so we cannot put -1 here. Ooh. So we could say push constant 1 neg. That'll work. You know, and like maybe if this is annoying to you, that every time you have to compile true, it takes 2 VM instructions. You could try to do clever things like maybe at the very beginning of the VM code you generate, you put the value -1 in some particular memory location, like in, you know, temp something, and then every time that you want -1 on the stack, you know that you already have it stored somewhere, and so you could just say like, you know, push temp 3 or whatever it is. But this is fine for now. So this is push true, this is And then we're gonna call output.print int 1, as one argument. Okay, now what?
Bless you.
Well, okay, down here I can put the code for, so this is push constant 0, this is push false. And then we can say call output.print int 1. What else do I need to do? This is not complete.
Yeah, so I need, like here, if we go here and we execute this code, we need to now jump past this code, right? We don't want to keep going and do that code also.
So I need to put another label down here. We'll call it like if end 1, 2, 1. 1 is good. And then we'll say go to if end 1. So yeah, this
This jack code here, which is, I mean, it's kind of 5 lines of code, but it's really just kind of 3, right? It's like the else, this part is super boring. It's just like we have this expression and we have this, else this. It turns into all of this VM code with a bunch of jumps and labels, and it's like, ugh. But this is how, if you just have the ability to like set the PC to something else, this is what you have to work with, you can jump. And originally, this is how people wrote code. But it's kind of messy. So, all right, let's think about how we will, okay, I'm not. So this is something like, elif token equals if, compile if. Okay, and then let's compile an if. All right, so we're gonna, so we've already read the token if, and so let's look again at the syntax here. I guess I didn't write it down, so if statement. Syntax for an if statement is if, and then we have required parentheses, and then an expression, parentheses, and then a curly brace, followed by statements, curly brace, and then else, curly brace, statements, curly brace, question mark, because the else part is optional, right? So in our example here, we did have an else, but we're going to have to think now about what do we do if there isn't an else. We've got to be able to deal with that too. Let's see, just make sure. Yeah. No semicolon. Some languages, such as Java, don't actually require, if you only have a single statement, they don't require curly braces here. That's actually not too much harder to deal with, because basically, the way I would do it is I would say, I would define something called a block, and a block, or no, sorry. Yeah, I would say a statement is either, one of these types of statement, like an if statement, a let statement, blah, 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 or it could be a block. A block, which is like a single statement, consists of some curly braces with multiple statements inside of it. And so, just like when you have an expression could be, well, it has a term, and a term could be parentheses with another expression inside of it.
say a statement could be curly braces with more statements inside it. And that's how Java does things. That's why, except kind of, not exactly. That's why in Java, if you have an if statement, if you only have a single statement inside the then part, you can actually leave out the curly braces, if you knew that. It's not super consistent about it though, because in Java, if you have a function definition, even if your function definition is only one line, you cannot leave out the curly braces. I don't know why, but okay. But in Jack, curly braces are always required. So let's. All right. So we already read the if token. We're going to skip the parentheses token, and we're going to compile an expression. That's the test, right? And then if we look over here, right, we compiled the test, but then we also emitted a not, because we wanted to flip it so that we get our jumps the right way around, right? So we'll just say emit, and then we're going to skip the parentheses after the test. And then we're going to skip the opening curly brace. Let's think about this. So before we do that, actually, let's think about what we want to do here. So this was the test and the not. The next thing we needed was we had this if goto that jumped to if else one. So and maybe we have a few options. One, we could keep reading tokens until we figure out whether it's an else or not, but that's going to be awkward because the way that we're going to read through the then part of the if statement is actually we're going to call compile statements, and it's going to be emitting VM code. So at that point it's too late. So we'll just call the label if else, but maybe there isn't an else, and that's okay. So then that label will actually just be like at the end of the if statement. So we'll say else label. We'll say make label if else, right? And make label is gonna use some global counter, increment the counter, and put the number on the end or whatever to make a unique label. So make unique label. Okay, and then we need to emit the if goto, right? So we say emit something like if goto else label. Okay. Now we're gonna, of course, skip this, and we're gonna compile statements, and then we're gonna skip. So that's easy. What are we gonna do now?
Go to if end one.
What was that? Go to.
If end one.
No. I'm not sure if we want to do that or not. Because the thing is, if there isn't an else, right, then we don't need to do a jump here because we're already at the end, right? We'll just need to put that if else label so that we could jump past the then part if we need to, but we don't need to do another jump if we don't have an else part to jump over. So how do we figure out if there is an else or not? What was that? Peak. Yeah, we want to use peak because if there isn't an else, then who knows what that token is, and we don't want to mess with it. So, let's say peak. Actually, I'll just say if peak. Why do I keep typing pook? I don't even know what it is. If peak is
the next token is actually an else keyword, then, okay, let's think about this else case first. So if there is not an else, then what do we have left to do? There's actually, I think, only one thing we have to do. Sammy?
Do we just omit the else label?
Yes, exactly. We need to omit the else label so that we have somewhere to jump. If there isn't an else, then we just need somewhere to jump. This needs to have, a target to go to. And this is part of what makes this so confusing, is that like, we have to kind of, you're like, okay, if this, then we're gonna jump past this, but then you need to do some other stuff first, and then eventually, like, at the right time, emit the label for where you wanna jump, but it's like, it's all interleaved together, right? An actual if statement is nice, because it just lets you think about things kind of like in atomic chunks. You're like, okay, well, here's the test, I can think about that, okay, and then, here's the part I wanna do if it's true, here's the part I wanna do if it's false. They don't like interleave in any funny way, but when all you have is go-tos, then you kind of have to keep track of everything that you're doing all at the same time. So we're going to emit label, oops, else label. Okay, but if there is an else, then what do we need to do? Well, now we can actually just look at this example and think about it. So basically, we just finished doing this part. So the first thing we need to do, of course, is we need to generate another label for the end of the if and emit that. So we'll say end label equals make label if end. So I don't know, depending how you do this, maybe it would end up saying if end 2. And it's up to you whether you want to, you could make the labels kind of both at once so that they would have the same number, and then it would be a little easier when you're reading it to know that they go together. But it might be simpler to just, if you just always call make label every time you need a label, you'd have like, if else 1, if end 2, if else 3. Doesn't really, as long as they're unique, it doesn't matter, but. So then we'll emit go to end label. Now we can actually emit the else label. Okay, so this is like skipped else part. And now let's see. We'll do something similar to this, right? We skip curly braces, we compile statements, skip that curly brace, and then we finally have to emit the actual label for the end label. Make sense? Okay. Any questions about ifs?
what if, in these statements, there was another if statement?
Yeah, it's just what
Would
it
we
is.
need to do anything special to handle that, or will it just work? Daniel thinks it'll just work. It's very complicated. It should just work. Again, as long as we're making sure that all our labels are distinct. You know, it's okay if we've got a bunch of code for some if here. If that's inside of a bigger if, it'll just like jump all the way, you know, past it or whatever. It might be hard to tell just from looking at the generated VM code whether you have nested ifs, because it doesn't kind of show you any nesting. The only nesting that's apparent is if you kind of match up the go-tos and the labels and like figure out, oh, this is like a thing because it says jump here and it's down here. And I guess that's an opportunity to say that remember that I guess I'm putting comments here, kind of like comments for us as we're writing this VM code by hand to kind of remind us what we're doing. However, like you literally can have comments in VM code, right? So you should feel free if you want to add some, you know, emit some comments as you're compiling things. Just so that when you look at the generated VM code, it helps you to like see what, you know, where the different pieces are. You know, you could say, oh, we're compiling this if statement, or we're compiling a while loop here, or whatever it is. So that could be especially helpful if you're trying to debug the generated VM code. Like you're not quite generating the right code maybe, and you're trying to figure out, you know, what's wrong. So having some comments can help you to find the right place to look at. All right, let us look at yeah, okay, so alpha show has so this is another test case for project 1011C. So it's just got a single function, right? It's got a couple local variables, let statements do. Really the only extra thing it has that we didn't already see in the previous test is that it has a while loop. I guess it also has like the not symbol greater than. Those are easy. So I'm not going to write out the VM code for this entire thing, but I do want to think about just what VM code would we want for this while loop. So we'll do the same thing. We'll figure out what some appropriate VM code would be first, and then we'll figure out how to write some pseudocode for the compiler to compile while loops. Thankfully, while loops don't have an optional else part unless you're in Python, so we don't have to deal with that. So here is the VM code for while loop. All right. So what do you think? How might we start? What might the VM code for the while loop start with?
Expression.
What was that?
Expression.
The expression? Yeah. So probably we'll just. So here's the VM code for the while test expression. It's going to be something like, you know, push, let's see, counter is probably going to be local 1, because target comes first, so that's going to be 0, and then counter is going to be 1. So it's like push local 1, push local 0, greater than not, right? So this not, we're going to say not. Okay.
So if that is true, then we want to actually do the stuff inside the while loop, right? So how should I go about that? Well, if it's true, I want to do the stuff in the while loop. And if it's false, then I'm done. I want to skip past everything in the while loop and continue with whatever's after that.
Treat it like an if statement with no else.
Yeah, so, wait, say that again?
At least for now, treat it like an if statement with no else.
Treat it like an if statement with no else, okay. Yeah, it's gonna be similar. And in particular,
What might I want to do with the result of the expression? Because, you know, maybe I'll have a label at the end that's like label while and, you know, let's say 17. I'm definitely going to want some kind of if go to, right? But like, is this what I want? Simon?
You need another not.
I need another not, right? Because if it's true, I actually want to do this stuff in here. If it's false, I want to jump to the end. So I need to invert this. Now, it's a little silly having not, right? However, it's fine. I don't expect you to, deal with that. It's a nice opportunity to say, like, there's different ways that you can optimize, the output of your compiler. And you can optimize at various different levels. You can try to optimize the Jack code kind of before you emit code for it. You can emit a bunch of VM code and then look through it and kind of look for opportunities to optimize it. So that's something called a peephole optimizer that would take the emitted VM code and look through it and say, okay, I've got several patterns that if I see this pattern, I'm going to replace it with something better. So certainly if you see 2 nots in a row, that would be a good one. Just delete them, right? And that's guaranteed to be equivalent. But it's easier to do it that way than to try to, do it right in the compiler when you're doing it. Because you'd have to be like, okay, I have to keep track of whether the last instruction that I just emitted was a not. So that if I, am in a while loop and I can see like, oh, if I want to output a not, maybe I should have undone that or something. I mean, it's much easier to just like generate the code, and then you can go through and try to optimize it. So I'll say it's weird having consecutive nots, but optimization comes later. And you're not at all required to optimize the output of yours, right? Just all right. So if okay, so now we said, all right, if the test was false, we're going to go to while end, and now we just need to compile the code that goes inside the while loop, right? So we'll say, something like push local 1, that's counter, and then we'll call output.print char1, and then we'll compile this let statement. It's probably going to be something like, we're going to say push local 1, push constant 1 add, and then pop local 1. This is going to be counter, push counter. Okay, now what? Yeah, so when I get to the end of a while loop, I need to go check the condition again, right? So I need to do like an unconditional jump back to the top of the loop. So I actually needed a label up here because we need to be able to jump back to it. So while start.
And then at the very end, I'm going to say go to while start 17.
That make sense? So in some sense, while loops feel to me a little simpler than if statements. Maybe it's because if statements can have the optional else part, and that somehow that just makes them trickier to deal with. But this is, I mean, there's different ways you could do this. For example, you could put the test code at the end, and then at the beginning of the while loop, you could jump down to the test code, and then have it either continue if it's false, and then jump back to the to the start of the while loop if it's true or something, and then it'll just like continue on and do the test again. That'd be an interesting way to do it actually. Then we don't have to do the not. We don't have to flip it, because then you do want it to actually jump back if it is true, and continue past the end if it's false. The problem with that, of course, is that now you're generating code out of order. So you have to first generate the code for what's inside the while loop, then you have to generate code for the test. And again, the way that we're writing our compiler makes that annoying and difficult, right? Because basically it's because of the idea that we're kind of parsing the code as we're emitting VM code. And I think I mentioned that real compilers don't work this way, right? Real compilers have two separate phases, where they first read in the entire program and build like a tree that represents the program, and then they emit code for it. So that makes it a lot easier for real compilers to do things like generate code that's not in the same order as input code. But we're not going to do that. We're not going to do that just because then we have to talk about, okay, well, how do we represent trees in Python or whatever, and how are we going to, it's cool and it's worthwhile learning about, but it would just be like one thing too many. Okay, so that's that. So let's quick write up some pseudocode for this. So while if, right, so elif, we have a while statement, compile while, and right, we'll have elif other stuff. We'll put compile while down here. Compile while, yeah, it rhymes. I guess I did not actually write the syntax for while up here, but I will do that now. It's pretty simple. It has the keyword while, and then a parentheses token, an expression, parentheses, curly brace, statements, curly brace. That's it. Easy peasy. So compile while, we're gonna say, we'll skip the parentheses, compile the expression. We'll, no wait, I forgot something, but we'll come back. I'm just thinking about this. We'll emit the not to invert the expression, right? And then, well, what did I forget? I forgot this label that we needed to start, right? So let's make some labels. So we'll say start label, let's make label, while start. And we might as well make an end label while we're at it, because we're definitely going to need both. And then I'm going to say emit, label, start label. Okay, then I do the test expression, do the not, and then we say we're going to emit this like if go to while end, or end label. And what comes next? Now we do all the, we're going to skip the curly braces, we're going to compile the statements, we're going to skip this curly brace, and then we just need two more things. We need the go to and we need the label. So we'll say emit go to start label, and then emit label, like that. Cool. So that's
more straightforward than if, but it still makes me glad that we have while loops and I don't have to write go-to statements.
So, kind of as a fun historical aside,
so it used to be, I mean, obviously when people started programming, when people started making
digital computers and started programming them, they were programming them directly in machine code, which, you know, probably basically just had jumps, right, maybe conditional jumps. And then, you know, people pretty quickly developed assemblies that they didn't have to literally write like ones and zeros, but they could write, you know, but they still just, everything was just go-tos, right? And certainly people kind of quickly realized there were certain patterns that happened a lot. Like if you wanted to do a loop, you would just write this kind of pattern, right? But of course you could do anything else you wanted. So if you wanted to, you know, jump somewhere out of the middle of a loop, you could do that. You just put a label somewhere and you just jump. But that obviously can lead to pretty hard to understand code. You might have heard the term spaghetti code, and that really was where that idea comes from, because, you know, each thread of control as you're going through the program is like a strand of spaghetti. They're all tangled up because, like, well, this goes over here and this goes here, and then it can become really, really hard to keep track of what you're doing. But even as people were developing some higher level languages, so this would have been like in the mid-50s, all the high level languages that were developed still had go-to statements, because, like, of course, you need to be able to jump to somewhere else in the program, right? And actually people didn't even understand whether it was possible to, like, write programs without ever using go-to statements. So there were a couple things that happened. One, I think this was a little obscure, but it's, you know, it was obscure at the time perhaps. But some people actually proved mathematically, they published a paper where they proved that kind of any kind of control flow you wanted, you could do without using go-to statements, like without using jumps. If you only had, you know, if statements, basically, you know, conditional statements and loops. If you have conditional statements and loops, then you can do anything you want. You don't need jumps. And that is super familiar to us. Like, we kind of take it for granted. Like, you know, we never write jumps. We just write conditions and loops and stuff. But at the time, that wasn't obvious. And so they mathematically proved it was possible. And then this guy,
Oh no.
that's your Dijkstra. You might have heard of the name Dijkstra from Dijkstra's algorithm. He published this statement, this paper, which is a classic, and he actually called it something much more kind of sedate. He called it like a case against the go-to statement, or an argument against the go-to statement. But the publisher was like, no, we need something more spicy and controversial, so called it go-to statement considered harmful. And I'll put a link to this on the website. It's not that long, but he's not just saying, oh, like go-to is terrible and it you know, you shouldn't use it. He's making a careful, reasoned technical argument why having jumps in your program makes it very hard to understand and reason about. He was all about, basically at that time, there was kind of an attitude like, you know, you just, by hook or by crook, you got it done. You just figured out whatever tricks you needed to get done what you needed to get done, that's what you did. And you just kind of, you just figured it out. And there was almost like a certain pride in like getting things to work by using awful tricks, right? And he was a ways ahead of his time, but he was all about, he's like, no, let's think about programming as kind of a mathematical discipline where we need to be able to reason about the programs that we're writing, even like formally prove that our programs do what we want, maybe start with some specification of what we want and kind of derive a correct program, kind of by steps. So for him, something like like a go-to statement, like a jump, it just kills any ability to reason about what your program is doing, or it makes it much harder to reason about what your program is doing. Morgan?
Is it like the opposite of today, where like if you're the only one who can understand your code, that was good, like a badge of honor?
Yeah, kind of, right, exactly.
He's the reason we have readability.
What was that?
He's the reason we have readability.
One of the big reasons, yeah. I mean, it was kind of in the air, but I think when he published this, it kind of crystallized a bunch of things that some people have been thinking about. And so, at this point, basically, there was kind of this growing idea of what he called structured programming, which is programming where you just, you don't do things like jumps, you just use structured things like conditionals and loops. And it was already known at this point, theoretically, that you could do everything without using jumps. And so he said, look, we know that you can do everything without using jumps. And here's all these reasons why having jumps in your program makes them very difficult to reason about. So I think we should just get rid of it. Like, programming languages should not have it. Yes, of course there's going to be jumps like in the actual machine, but our higher level languages should not provide that facility at all. We shouldn't use it. And so that was very influential. Of course, I mean, so like the languages that do Python, Java, etc., do they have jumps? Well, kind of yes and kind of no. They don't have literally like a go-to statement where you can just go anywhere. However, if you have something like a break or continue in a while loop, that is actually literally giving you like a kind of jump. Although it's a little bit more principled than just having an arbitrary jump. And actually, it could be a fun exercise. If you wanted to, you could extend the Jack language to include break and continue keywords. It's actually very, very easy to compile. So the break, when you hit a break statement, it just compiles into go to while end, right? You have to keep track while you're compiling it of like what the current loop is that you're compiling, right? So that you know what label to omit, but that's not hard. And if you have a continue statement, that's just a go to while start. It just says, okay, I'm just going to stop this execution of loop, go back to the top and test the thing again. So, I don't know, probably like, maybe some of you in 150 tried to use break or continue or something and you were, got a slap on the wrist and don't do that. Honestly, sometimes they're exactly what you want. And they are kind of giving you a principled way to do certain types of jumps in a very controlled scenario that, anyway. So, there's something else I was going to say. Now I can't remember what it was. I don't know. Any other questions? Maybe I'll think of it. Simon?
Would it be too difficult to add a do while loop?
That wouldn't be difficult. Yeah. You'd have to think a little carefully about like exactly how you arrange the VM code to give you the right behavior. But probably it would literally just be like, you would have the code for the body of the loop, and then you have, the condition comes at the end of a do while, and you would literally just put the code for the checking the condition down there, and then it would, it would jump back to the top if it was true, and it would continue if it was false. So that'd be pretty easy, actually. Yeah, and you could think about like there's other kinds of, you could have like until statements, which is just like a not, but it flips, false to true, and that's easy to compile too. So all these kind of typical loops that you have compile. So the more interesting thing to think about might be if you wanted to add a for loop to the Jack language, which it does not have, right? How would you compile that? And it's not ultimately that hard either, but it would require a little bit of thinking how you want to do that. All right. So I think, oh, wait, is that not linked yet? Oh, okay. There should be a link there. It's up. I mean, if you go to this one, it's there, but, anyway. But, yeah, so 1011C is due on Monday. So you should have everything you need now to do that one. And then next week we're gonna talk about, compiling, the only thing we have left really is like dealing with classes and objects and also arrays. All right, see y'all on Tuesday.